everyone. So for me, it's a pleasure to be the chairwoman of the last session of the event. So we will have now the last session of the course of the transversality methods and its application with Balázs.
Thank you very much. And yes, we are now at the application stage. So today I would like to talk about a few applications in this regards. And but the applications won't really leave for me the iterated function systems world. But the first application, what you can use these simultaneous no dimension drop result is finding dimension maximizing measures. So basically, So if you use the previous system, so let me state it precisely. So let phi f of I lambda be a smoothly parametrized C1 plus alpha conformal IFS on RD. Okay, so all of the maps now C1 plus alpha conformal and smoothly parameterized. So if you don't want to imagine what the smooth parameterization is, for example, feel free to think about the case when we use the parameters as the translations. Okay, the index set is A, and where this set is from where. So we are in RD, and we have as many coordinates as many functions we have. So that space, this translation parameter, Fi's are C1 plus alpha conformal on RD, and think about the parameterization Fi plus these randomly chosen translation parameters. And also what we assume that the GPS holds. So this generalized projection scheme holds, which in our case means that if you take the sum of, I don't have enough space. So if you look at the subnorms of the derivatives. Oh, this generalized projection scheme from the previous one. There is a bunch of conditions what you need for smoothness, something like that. So I don't want to repeat it. Yeah. But feel always, if you don't know what GPS is, feel free to think about that you have some fixed maps and you apply translations as parameters. That will be always good. And what we need is that the sum of the contracting ratios should be at most 1. Okay, this is always GPS. Okay, so in this case, what you have is that then for Lebesgue, almost every choice of the parameters, there exists a mu measure, mu ergodic shift invariant, such that the Hausdorff dimension of the push forward of this measure equals to the Hausdorff dimension of my attractor equals to S naught of lambda. And I will tell you in a minute what these notations are. So this lambda is pi of lambda is the natural projection from the symbolic space to RD. The x lambda is the attractor. Oh, I should write here differently, sorry. Minimum of 1 and S naught of lambda. So x naught is the attractor, my unique invariant compact set, and also S naught is the Hausdorff dimension on the symbolic space, which is the smallest s, such that if you sum up with respect to every finite composition of the derivatives to the power s, this sum will be finite, which means that this is exactly my dimension with respect to the metric, what you get with respect to the derivatives on the symbolic space. So this does not drop. Furthermore, if this S naught lambda value is at most d, then this mu measure is unique. Okay? And this basically follows from variational principle. And of course, this lambda measure then depends on the choices depending on lambda. But what do we know? If we have the GPS, then with respect to this nice associated metric, every ergodic measure has this regular dimension separability. So there is no ergodic measure of which dimension would drop. So in particular, what you get from the variational principle for the standard potential, it won't also drop. But also what we had, some absolute continuity result, but it's a different one with Károly Simon, Boris Solomiak, and again Adam Spiewak. When you are on the line, so all the same system except that you are on the line, and S naught lambda is strictly greater than 1, so I'm only restricting my interest those set of parameters where this S naught is strictly greater than 1, okay? Then this equilibrium measure is absolutely continuous with respect to the Lebesgue, and it has L2 density. So which means that not only we know that it's absolutely continuous, we also have some regularity properties about that. Unfortunately, not much more. So in the case of self-similar systems, yes. In that case, it's unique. Okay, it depends on what do you mean by uniqueness. It's the unique measure, right? If you think about in the symbolic space, it is the unique measure for which this S naught value equals to the entropy over the Lyapunov exponent. In this sense, it is always unique. Of course, if my dimension exceeds the dimension of the state space, then my dimension maximizing measures won't be unique. There will be a bunch of guys above this plateau. But on the symbolic space, it's unique. And I meant this measure here. Yes, exactly. That is exactly the Gibbs state for the potential minus log the derivative at I1 pi lambda sigma I. And I think I need to normalize by S naught of lambda. So this is exactly the potential. And it's nice, Hölder continuous, although it's a parameterized family of potentials, still the variational principle, everything we know. We know everything about this measure. So yes, it's a Gibbs. Thank you. Okay? So in the case of self-similar business, we have better results. So what do I mean by self-similar? Again, that my maps are these linear maps on the line. And in that case, what we know that there exists an exceptional set of let's say the translation parameter. It can be again formalized more generally, but let me formalize only for translation parameters, which has dimension at most n-1, such that if you choose your translations out of this set, then, if you look at the natural measure, who is the natural measure? The natural measure is the Bernoulli measure with the probabilities Ri to the power S naught, where this S naught is the same S naught, right? Except that in this case, we can really formalize it that S naught is the unique solution of this equation. And if you look at this Bernoulli measure, and you assume that S naught is strictly greater than 1, then its projection is absolutely continuous with respect to the Lebesgue with LQ density, Q strictly greater than 1, and this is good for every Q. Yes? Yeah, this is the exceptional set. No, Hausdorff dimension is at most n-1. So what you know is, no. No, sorry, I'm stating it wrong. No, you're absolutely right. No, I'm making mistakes here. No worries. I'm making here mistakes. Let's put in the following way. Okay, let me only state that the special case, I am certain at the moment that the contracting ratio is the same for everyone. This means my measure is the uniform Bernoulli measure. And what I want to say that there exists a set of Hausdorff dimension 0, such that whatever you choose your R out of this set, right? I want also absolute continuity, so I need that this contracting ratio is greater than the number of the functions, 1 over n. Capital N should be the number of the functions. Okay, so there exists this choice, such that there exists another set of RD, who are the translations, such that however you choose your translations from this set, then this push forward measure is absolutely continuous in LQ density for Q greater than 1. So what you need to choose is choose the contracting ratio typically, and also then choose the translation parameters typically. Then where you end up in the regime where you expect that the dimension is strictly greater than 1, absolute continuity with density for every Q. This is the result by Schmerkin. Saglietti, Schmerkin, and Solomiak. Okay, so this result. Yes, that it doesn't rely on transversality method. It relies on this exponential separation LQ dimension stuff. Yeah? Usually?
When the dimension is exactly 1.
Oh, yes. If it's exactly 1, then typically it won't be absolutely continuous. Because if it's exactly 1, then what you expect is that your system will be R-force regular. But in the case of overlaps, then you don't have R-force regularity. So, or if the contracting ratios, let's say exactly 1/n, then either you have open set condition, and then you are absolutely continuous with the best regularity option, or you have overlaps, and then the Hausdorff measure is 0, the measure must be singular. So at the phase transition point, any 1/n equals to, R equals to 1/n, there are different behavior. Okay, so what I wanted to say that, you can find these problems, you can find dimension maximizing measures with this general projection scheme and using this dimension regularity of the ergodic measures. But also there is another application I would like to tell you is the multifractal analysis. And for this, I will restrict myself to this self-similar word. And also in this self-similar word, I will restrict myself on the real line. So Ri is some positive and smaller than 1. And I also assume that the sum of the contracting ratios is strictly smaller than 1. What does this mean? My attractor is expected to have dimension strictly smaller than 1. This is what this condition means. And if you take a measure mu, who is a Bernoulli measure on my symbolic space, I project it down in the usual way. So I have my natural projection. Right? Then we know that for almost every point, right, we know that the dimension of this won't drop in 2 situations. Right? This is, then I know that this is the entropy over the Lyapunov exponent. Who is lambda? There is no lambda. Yes, thank you. At the moment, there is no lambda. Thank you. Yeah. So you know that it is equals to the entropy over Lyapunov exponent, this dimension. In 2 situations, basically, if you have strong separation or you have typical choice of translations. And what does the dimension mean? The dimension means that for almost every point, if you're looking at the local dimension at x, it equals to this entropy over Lyapunov exponent. This is what it means. But the question is that there might be and there must be other points, a huge family of points, where this local dimension is atypical, takes another value. So my question is, what can we say about the set K alpha if I have a given IFS mu, a given Bernoulli measure mu? What can I say about those points where the local dimension of this measure equals to this per given value alpha? Can we describe this function which describes the Hausdorff dimension of this set? Yes. In the case of the strong separation condition, it was done by Cayley and Mauldin. I forgot to write the date, but I think 92. And also, it was generalized a little bit further for the open set condition. If you don't know what's the open set condition, ignore it. But it was further generalized by Arbeiter and Paczke. And the answer is very nice, and at that time was quite surprising, and I think some people also called this as the multifractal miracle. Because, first of all, there are certain values of alpha min and alpha max, which are natural values, right? What is this entropy over Lyapunov exponent? I am about to defining this alpha min and alpha max. So what are these certain values? Because this is the entropy over the Lyapunov exponent, right? By definition in this case. And how do we get this? We get that we take the limit as n goes to infinity. What is the logarithm of the products of the probabilities of some certain cylinder set divided by the logarithm that what is the diameter of that cylinder set on the symbolic space, right? Because now my metric on the symbolic space is associated with these contracting ratios, right? This is the definition, by definition, the local dimension of the symbolic space. And then it's clear that this alpha min and alpha max shouldn't be anything else than the smallest possible rate of the log pi divided by the contracting ratio, and alpha max should be the maximal possible value, Ri. And if you out of this set, then of course no limit, this limit cannot be taken the value alpha, so then this K alpha set is simply empty. On the other hand, for alpha values coming from this alpha min and alpha max, the Hausdorff dimension of this set is the infimum. So it's a Legendre transform of some certain function tq, and I tell you what the tq is, where it is the unique solution of the following equation, pi to the power q ri to the power tq equals to 1. Okay, so it's a certain pressure. Right, so if you want to see how this tq looks like at 0, it is exactly the S naught. Right, where is the S naught? I should have defined somewhere. Okay, I will define it here. Right, S naught is that dimension. At q equals to 1, it takes the value 0, and otherwise it's a nice, strictly decreasing, strictly convex map. And what do you see? What is its Legendre transform? Then it is this alpha min, alpha max values. At the endpoints, it might be positive, might be 0. Anything can happen on your setup. But it looks like something like this. Okay, and there are two main points here. The first one, where it's tangential to the identity map. So this is what you see here, the alpha, here, the dimension k alpha. And where it's tangential is exactly the dimension. So this is exactly the dimension of my measure mu. And there is one value where it's maximal, takes this value S naught. Let me call it by alpha hat. And alpha hat also has this nice formula. This is Ri S naught log pi divided by Ri S naught log Ri. And from this, you can see the answer. What this alpha hat is the typical value of the local dimension with respect to the measure generated by this RIS naught probabilities. So this natural measure. And this map is analytic. So it's really a miracle that there is some object which is absolutely fractal-like, and at the end you press out of this some very, very nice analytic function. I really like it. Okay, but our main question is now, what can we say? Yes, please. So everything is just like here, and you assume the strong separation condition. Yes. I am on this word, and I'm even, this theorem would be good in R3, RD, but just for simplicity, I'm on the real line. So this is a collection of contractions, of similarity contractions on the real line. And furthermore, I assume that the strong separation condition holds. So for the invariant set, these images will be disjoint. Okay, these are the standing assumptions. After that, it's a beautiful calculation. Okay, and but this calculation relies on the following. Look at here. I have my measure mu here, right? The measure mu has some given probabilities. If I see something which sums up non-negative values up to 1, then I think that this is immediately must be a measure. So you define a measure nu q, who is a Bernoulli measure, and the Bernoulli measure exactly corresponding to these probabilities. And what allows you to analyze this K alpha set is the following statement, that the dimension of my measure mu is alpha if and only if the dimension of this nu q measure at the same point is q times alpha plus tq. And when does this happen? Well, basically, if you check that what is the Hausdorff dimension of this push-forward set, so basically you just check what is the local dimension of the symbolic space, you get that this is minus q times the derivative of tq plus tq. Right? Simple calculation gives that to you. So what do you need? If I want to understand what is this alpha value, what is this set for this given alpha, I'm searching for such kind of q where this minus derivative equals to this alpha. And this is how the Legendre transform comes into the picture. Okay? Because how do you minimize this? The minimum achieved where the derivative of at q equals to minus alpha. So it's an easy calculation, and it comes from the strict convexity. So it's a very nice trick. But the question is, what can we do if we have overlaps? Because if we have overlaps, there are two enemies in the way, but the methods of Hochmann, Schmerkin, deals one difficulty, that we know that the dimension of measures do not drop, right? So I would know that this dimension value. Yes?
Perhaps a very silly question. Returning to this informal case, would you, no, thank you. You have here a one parameter family, blah, blah, blah.
It's not necessarily one parameter family. It's,
Let me think about
yeah, okay.
the family. When you move the parameter, do you know if the dimension change continuously?
Yes. It's coded in the assumptions. So this is why I need also smooth parameterization. Yes, so I need the parameterization. For example, the parameterization needs to be so smooth that this guy changes continuously, for example. Yes, it's coded in the smooth parameterization. You could, of course, define worse parameterizations, but then I don't know what's going on. Hmm? Okay. You're welcome. Okay. So we want to deal now with overlaps and, oh my God, and basically relying on very heavily of the result of Pablo Schmerkin on the LQ dimension, and I still don't want to state for you what the LQ dimension is, there's a theorem by Bárány and Feng, and I again missed the date, but if this phi IFS on the real line I just described you has this exponential separation condition, and you also assume that the sum of the contracting ratios is strictly smaller than 1, which is, as I said, equivalent with the dimension of this set being strictly smaller than 1, no matter what happens, then they showed that the Hausdorff dimension of this K alpha is given by exactly the same value, but only for alpha values coming from the interval alpha min and alpha hat. What does this mean? Relying on Schmerkin's result and lots of other very nice things, what they verified that even in the overlapping situation, you have this increasing part of the spectrum. Okay? But if you wish, if you're willing to sacrifice the exponential separation condition, then you can get the whole spectrum. Of course, this is just a special case of Bárány and Feng, so they have a more general setup. I just stated here the corollary for this system. But we showed that under the same conditions, for Lebesgue, almost every choice of the translation parameters, the Hausdorff dimension of K alpha is what you expect it should be for every alpha between alpha min and alpha max. So you can have the full spectrum. Okay? So this thing relies also on two things. First is the simultaneous no dimension drop, which means that we know simultaneously for every ergodic measure that almost surely for every ergodic measure there won't be any dimension drop. So what we would know that typically the dimension of the push forward of this nu q measure is what it is. It's minus q tq derivative plus tq. So this is what we know. But the second part, which is also required, is missing because I also need to understand that the local dimension of this projection of the mu measure at x can be alpha if and only if the local dimension at this nu q measure equals to q times alpha plus tq. This is the next step which is missing. Yes? For all ergodic measures. On the entire set, yes. Yes, if you choose the typical parameter, then no ergodic measure is there for which the dimension would drop. Yes, it's absolutely simultaneous. There's a wider family of such measures, but I don't want to redefine it. It's quite technical something. Okay, but I would like to also understand that the local dimensions behave as they should behave. And then the third step will be an upper bound But usually the upper bound is just using the Lipschitz property and covering the set. So that's the easy part. So let's see what can we do for the second problem. So what can we do to solve this thing? And for that, you can have the Eddy phenomena, which is the exponential distance from the enemy. I tell you what it means. It says the following. For a point I in the symbolic space has exponential distance from the enemy if for every epsilon greater than 0, if you look at what is the distance of this point from the following set, from the set which takes the union over every n-length cylinders who are not the first n symbol of this sequence I, you are looking at the image of these cylinders, and this distance is at least, well, whatever the diameter of my cylinder should be, so Ri, first n symbol of Ri, right? This should be the diameter of my cylinder. Of length n containing this point, times e to the power minus epsilon n for every n sufficiently large. So whatever epsilon error you take, after some certain time, this guy will be far from all the other cylinders. Is it clear what it means? So basically, it's not only says that this point is in not only other cylinders, which are not corresponding to its first n symbols, I also can establish that the distance is almost comparable with the size. And basically, what you can show is the following. I'm searching. That also for the exponential distance from the enemy, for this Eddy condition, you have simultaneous property. So for Lebesgue, almost every translation parameters, for every mu ergodic shift invariant measure on my symbolic space, for mu almost every infinite sequence I has this Eddy property. This means the following. This again holds simultaneously because you fix your random translation parameter, then you would know this Eddy property holds for typical points with respect to any ergodic measure. So only the very, very irregular points are which can be bad. But what does this mean? Look at here. I am trying to calculate the local dimension of at some point. So I take, so let I be mu typical. So I'm trying to take the local dimension at this point, pi of I, of what? Of any measure. So let nu be any measure. Really any. What does this mean? But the center is mu typical. The center is mu typical, but I'm looking at the local dimension with respect to any measure. What does this mean? What it is? So this is the limit if it exists, otherwise it's lim in for lim sup, of the measure of the ball with radius r divided by log r. Also, I can take this limit along subsequences. So I can just simply take the limit as n goes to infinity log of the ball at this measure, the ball at pi with radius r in, the diameter corresponding to the cylinder divided by log r in. But look, what do I know? I can freely add here an exponential error, right? If instead of this RIN, I would add here this exponential error, e to the power minus epsilon n, and also here, then what would I know? That this ball doesn't intersect any other set of any other cylinder other than the cylinder corresponding to the first n symbol of I. So what do you know? This is at most what? The limit as n goes to infinity, the logarithm of the cylinder of I up to n divided by what? There is this minus epsilon error plus log IRN. But the epsilon again was arbitrary, right? After some time it would hold. So what did we get? Because this is the upper bound. Always the upper bound is the bad guy. No, this is the lower bound. This is the lower bound. Sorry, my bad. This is the lower bound. And always the lower bound, the bad guy. The upper bound simply follows by observing that this map, I'm talking about the natural projection, is what? Lipschitz continuous. Okay, so this upper bound from here to that is straightforward. This one requires the exponential distance from the enemy. But the epsilon ones, again, arbitrary. So what we ended up, that in order to understand the local behavior on the line of any measure at some point, at some typical point with respect to mu, it's absolutely enough to understand what's going on the symbolic space. And this EDE exactly means this condition. Right? Because then I will choose my new measure to be my mu measure here. And it really follows that my local dimension with respect to mu equals to some pre-given value alpha if and only if my local dimension with respect to mu q is that value. Okay, so with this exponential distance of the enemy, we can handle this problem. But this exponential distance from the enemy really requires that property. That what you are projecting from the symbolic space does not exceed the dimension 1. Has strictly smaller dimension. Otherwise, we don't know that. Okay. And I think I have 3 minutes. Is that correct? Yes. So since I still have 2 pages to say, I think this is the best time to stop. So thank you for your attention for the full